In this first video in the series of digital signal processing, let's look at what a signal is and also some foundational concepts of an analog signal. This will be helpful as we dive deep into digital signal in the future modules. Let's say we measured the temperature once a day over a week. This is a discrete signal because it gives us information on how the temperature changed over the week. It is discrete because we only observe the temperature once at a random point in time in any given day. But in reality, the temperature changes in real time, even within a day. It is a continuous flow of information on how warm it is at any specific point in time. Hence, if we don't sample it, that is, if we choose not to observe it, then by nature it is an analog signal. So a signal describes the evolution of a physical phenomenon. It's important to note that a physical phenomenon doesn't necessarily have to be a natural one. It can be human made as well. As in this case, the movement of the S&P 500 stock market index over a period of time is also a signal. Time is not the only reference for a description of change. Space can be a reference too. As in this example, the measure of change in luminous intensity from a light bulb over an adjacent surface area is also a signal. Let's write a small Python code to visualize a simple analog signal, which is a sine wave. I'll put a GitHub link to this code in the description of this video. This signal has 3 degrees of freedom, which means we can control 3 variables that will change the generated signal. We can change the amplitude, which is A, the frequency F, and the phase shift phi for this signal. Let's plot a sine wave with a frequency of 1 Hz, amplitude of 1 unit, and a phase shift of 0. Let's now execute this code to generate our plot. Now that we have our plot, let's look into the definition of certain fundamental terms regarding the analog signal we have here. First is frequency. Frequency is the oscillations or complete cycles per second. A cycle is considered complete when the wave finishes a phase shift of 360 degrees or 2 pi radians. We'll see what a phase shift is later. For now, we can consider a cycle as the formation of a single pattern in a repeating patterns in the waveform. In this plot, we have one oscillation per second. So the frequency f of the signal is 1 Hz. Hertz is the unit of measurement for frequency. To elaborate further with an analogy, let's assume the signal describes a single oscillation of a pendulum. A signal is considered complete when the pendulum returns to its initial position after a move in one direction. Next term is wavelength. To describe it, let me create a new sinusoidal signal with a frequency of 2 Hz. I also plotted another wave of 4 Hz. Wavelength refers to the measure of how far a signal has traveled in a medium when it completes a full cycle. It's denoted by the symbol lambda and measured in meters as it is a unit of distance. In a periodic signal, we usually measure this as the distance between two crests. Crests are the two consecutive high points in the signal in terms of magnitude. When we compare the wavelengths of the 2 Hz and the 4 Hz signal, we can notice an interesting correlation between frequency and wavelength. Frequency is inversely proportional to wavelength. That is, as frequency increases, wavelength decreases. For electromagnetic waves propagating in vacuum, frequency is the ratio between the speed of light c and the wavelength of the signal. In other mediums, it is the ratio of the phase velocity v and the wavelength. Phase velocity measures the rate at which a signal propagates in a medium. Finally, let's look at what a phase shift is in an analog signal. Phase shift is the displacement of the waveform in time. Here we have displaced the waveform by half a wavelength. That corresponds to 180-degree phase shift. Since we are using radians as the unit, we change the phi variable to the value of pi in our code. 1 radian, denoted by the symbol pi, equals 180 degrees. We can displace the waveform to the right by assigning a positive value to phi. Assigning a negative value will displace the waveform to the left in relation to time.